Hey, let's talk about multi-message indistinguishability. So in the lecture, we've seen this multi-message indistinguishability game, which is basically your run-of-the-mill public key eavesdropping game, which is the thing that we use to define CPA security for public key encryption. It's just that this time, the adversary doesn't output a single message, but a vector of messages, or rather two vectors of messages. And then the challenger chooses one of them randomly and encrypts each of the messages individually using the encryption scheme, and then gives the adversary this ciphertext. And we've proven that if my encrypted scheme is CPA secure, then also it has this notion of multiple message indistinguishability. And I want to talk about basically some intuition of this fact and the underlying proof. And now the way to argue about this is basically we have two worlds in this game. We have the world where we choose b equal to 0 and we give the adversary an encryption of the first vector. And we have the world where we choose b to be 1 and then we give the adversary an encryption of its second vector. So these are the two possibilities that our adversary will get when he gets the challenge ciphertext. He will either get an encryption of all of the M1 messages or an encryption of all the M0 messages. And now let's just look at this first ciphertext here. The encryption of M11. What kind of guarantees does this encryption actually give us in terms of security? Well, it's a CPA secure encryption scheme, so almost by definition, if we switch out this M11 for any other message, then no adversary will be able to notice this switch. So let's do exactly that. Let's just imagine we just switch out the M11, and let's just say we switch it out for M01, so for the message in the other vector. So we switched out these two messages. And now my claim is that actually no PPT adversary will be able to distinguish whether or not we give him this vector of all the M1 messages or this vector where we switched out the first message with the M0 message. So how would you construct an adversary that would be able to distinguish between these two cases? So to do this, we construct an adversary A prime from an adversary A that we suppose is pretty good at distinguishing these two distributions. So it's good at telling whether or not the first message is M0 or the first message is M1, if we also give in all the other messages. So then this A prime pretty straightforwardly works as follows. So essentially, we will just smuggle our challenge ciphertext into this first component of the ciphertext vector. We do this by asking our challenger for an encryption of either M01 or M11. And then we take this encryption and just embed it into this vector of ciphertext that we give to A. And now we have two cases depending on what B our challenger chose. If B is equal to 1, then we are in this uppercase, right? Where all of the messages that we have encrypted, they're all from the 1 vector. And if B is equal to 0, then we're in the second case, where the first encrypted message is actually M0. So overall, if A is able to distinguish between these two distributions of ciphertext vectors, and we output the same bit as A outputs, then we would also be able to distinguish whether or not this was an encryption of M0 or M1. And we can actually go on and do this iteratively. So now that we know that these two are indistinguishable, we can basically say, okay, I don't care about this first vector anymore. I started with this vector, and now I go on, change this. And well, I can do the same trick again. I just replace this encryption of M1 with an encryption of M0. And by the same argument, I can still smuggle in my challenge ciphertext now at the second position. I will be able to argue that because this is a secure encryption, nobody will notice this. And if I go on doing this, then eventually I will have replaced all of the messages in this vector where I started with all of the messages being from the M1 vector. Now I get a vector where I've replaced all of the messages with the M0 messages, and then I would get to this vector. where all the messages encrypted are the M0 messages. In the lecture, we gave these distributions names. So this was called H0, this was H1, this is H2, and so on all the way until HT. And we have just argued that no PPT can distinguish between H0 and H1, that no PPT can distinguish between H1 and H2, and so on, and that no PPT can distinguish between HT and EHT-1. And transitively, also no adversary can distinguish between H0 and HT, because otherwise it would have to distinguish between at least one of these pairs. But instead of having one adversary against H0 and H1, one adversary against H1 and H2, etc., we just have one catch-all adversary. This catch-all adversary essentially chooses a random index to basically guess which of these two hybrids it hopes that the adversary will distinguish. So in contrast to other proofs where we did index guessing, A prime will never learn whether or not it chooses the right index. There is no right index in this case. Instead, this guessed index serves as a tool in our probability analysis to basically being able to argue about these pairs of distributions. Okay, and that's the main idea of this proof. Take a look at the lecture notes for like the specifics and all of the probability analysis, which I'm skipping here. I just wanted to give you an intuition of what's going on here. Thanks and see you.